Lambda max is the wavelength at which the electron emits at the highest intensity when returning to the ground state of a previously excited atom. On an emission graph, it's set up as wavelength versus intensity, where intensity is the number of photons emitted at a certain wavelength relative to the total number of photons emitted. Wavelength represents the wavelength of the photon emitted, which determines the color of the photon emitted. The color controls the lambda max because each color has a unique set of emission peaks on the emission intensity graph. The color determines both the lambda max and the various other peaks that may exist on a graph. At a given lambda max, multiple colors can exist because the lambda max only represents the highest peak within an emission spectrum, not including all of the lower peaks that can contribute to the color of the substance. This can be seen in our data when both the red glow stick and the mixed glow stick solution have the same lambda max. The mixed glow stick solution has a second peak at a lower wavelength, but it still has the same lambda max as the red glow stick, with a lambda max at about 616 nanometers. Additionally, what determines the color that's emitted is most dependent upon the intermolecular forces of an atom. Depending on these forces of a specific quanta of energy will dictate whether the electrons within the atom will jump energy levels or not. For example, if an electron is further away from the nucleus, then less energy would be needed or would need to be absorbed for it to jump another energy level, as there are less attractive forces.
Electrons can be excited just as elevators are able to take people up to another floor. Elevators will go up and down to specific floors based on which button is pressed. Likewise, depending on the specific amount of energy added to the atom, the electrons will jump to a specific energy level. Additionally, just like an elevator, electrons will not stop between floors or energy levels, as they require a specific quanta of energy to jump. This is why peaks occur at specific wavelengths, because wavelengths are inversely proportional to energy. Electrons will not remain at the excited state and will return to the ground state, causing an emission of light. This is like when an elevator returns to the bottom floor to pick up more people. In other words, the ground floor of an elevator can be compared to an electron at its ground state. For the electron, it's more energetically favorable to be there, as the state requires the least amount of energy. Likewise, for the elevator, it's most likely to be on the ground floor, as that's where most of the people are. This analogy shows a flaw in one aspect, however, as for the electrons, a specific quanta of energy is required for it to jump to specific levels, and if an electron is farther from the nucleus, less energy would be needed to be absorbed for it to jump again due to the lower attractive forces. With the elevator, the floors are shown to be equal distance apart, suggesting the same quantity of energy to go up a floor, but this is wrong in terms of the electrons for the reason described beforehand.